Assalamu alaikum and welcome. In this video I'm using time series and I would like to check cointegration among time series and then I'll estimate the error correction model. I'm using Stata. I have already done such kind of videos in eViews, but now I'm using Stata for analysis of my time series. Now, before I do that, let me introduce some of the important steps that will be taken for cointegration. And this is a simple bivariate cointegration in which I'll relate two time series. So the first step is to verify that both of the time series variables are integrated of order 1. The second step is to estimate the cointegration equation, and after estimating the cointegrating equation, I'll verify that the linear combination is stationary by using Engel-Granger critical values. And finally, I'll estimate and interpret the error correction model. I'll be using these critical values instead of the conventional values of the cointegration test using Dickey-Fuller and other. So I'll do that. And first I'll estimate the long run model, and after that if there is cointegration, then I'll estimate the short run model and I'll interpret the error correction mechanism. And these are the two models that later on I'll compare. So let me have my file. This is my data file, and in this I have investment as one variable at level, income another variable at level, and there is consumption another variable at level, and finally I have set this data as time series, and this is quarterly time series data. Then I have converted the investment variable into natural log of investment, and this is the natural log of income, and this is the natural log of consumption, and I have also taken the first difference of the log of investment, the first difference of the log of income, and the first difference of the log of consumption. So let me clear this, and later on I'll create this again. So I want to drop this. So these two variables were dropped. So the first step in estimating or in checking cointegration is that the series should be integrated of order 1. So I start with the income. Income is my dependent variable, and I'm using Dickey-Fuller. I'm using Dickey-Fuller test to show whether my income variable, log of income variable, is stationary or not. And since this is in level, so this critical value is less than are these values at 10%, 5%, and 1%. So we fail to reject the null hypothesis, and the log of income is non-stationary, it has a unit root. However, if I check its stationarity using the first difference of log of income, then this p value is 0.00. So we reject the null hypothesis, and we conclude that the natural log of investment in its difference form is stationary, it doesn't have unit root, so it is integrated of order 1. Next, I'll check log of investment using Dickey-Fuller, and the p value is 0.67, which is greater than 0.05. So it means that this series, that is natural log of investment, has a unit root. It is non-stationary at level. Now let me check this using the first difference of the natural log of investment using Dickey-Fuller test, and here is the test result. The absolute value of the test statistic is much higher than these values, and the p value is 0.000, which is less than 0.05. So we reject the null hypothesis that the natural log of investment in its difference form has a unit root. So we conclude that when we take the first difference of the natural log of investment, then it becomes stationary. So both of the series, that is the natural log of income and the natural log of investment, are integrated of order 1. Next step is that let me check the graph of the two series, and this blue one is the log of income, and this graph, this purple one, this is the log of investment, and both the series are increasing. There is a positive trend, so they may be integrated, but we don't know as yet. This is just a visual view. After this, I'll run the traditional OLS, and I am regressing the natural log of income or the natural log of investment, and here are my results. This is the total sum of square, the model sum of square, the residual sum of square. F statistic is significant, R squared is 0.97, and this is the coefficient of the log of investment. It means that if there is 1% increase in investment, there is 1.15% increase in income, and this is constant, and both of the coefficient of the log of investment is significant. After this, I'll predict the residual for this regression, and U hat has been now generated, and these are the residuals. Let me check the statistics, the descriptive statistics of this residual. Total number of observations 92. This is the mean value, this is the standard deviation, minimum and the maximum value. And after that, let me check the graph of this. Here is the graph, and now the residual, there are some ups and downs in the residual, but they are moving around the mean of 0. So seemingly it seems that these residuals are stationary, but we will run the formal test. Now I'll use this Dickey-Fuller test on the residuals, and I'm asking the EVs not to use constant. So this is the Dickey-Fuller test for residuals, and this is the test statistic value in its absolute form. This is greater than all this, but remember, these are not the valid values, so we will use the Engel Granger critical values for this, and for that I will first run this E Granger natural log of income and natural log of investment, and these are the residual, and these residual have been created here also, E Granger residuals, and again this value is less than these. Now this shows that there is no cointegration. Seemingly there is no cointegration. If this value in absolute is much higher than these values, then we can say that there is cointegration, but there is no cointegration on the basis of this. So let us suppose that there is cointegration, that this value is much higher and there is cointegration, there is long run relationship. Then we will run this regression, and let me show this regression is this is the first step. We will regress this in long run, and these variables are non-stationary at table but co-integrated. Now let us re-estimate the short model. So I'll show that in a while. So I'm here. Now this is how we regress the short run model. And for the short run model, as I mentioned earlier, for the short run model, the variables should be in difference, that is in stationary form. And we need to incorporate the error correction term into the model. And this error correction term are the residuals of the long run model with lagged 1 period. So this is a lagged 1, and this is equal to natural log of income minus beta naught minus beta 1, natural log of investment minus 1. And if we then we have this equation in difference form, that is delta natural log income with lag 1 period. Then I regress this on delta natural log on investment in lag 1 period, and later on I have this as a error term, and if I plug this equation number 2 into 3, I get this. So I am basically going to estimate this equation. So let me go back to the Stata. So this is the equation that I just discussed. So this is my equation, and in this equation the F statistic value is 3.30 and it is significant. So overall equation is significant. The R square value is 0.067, the 0.069, and the adjusted R square is 0.05, and the coefficient of the difference of log of investment is 0.041, and this is not significant. And the error term with lag 1 period is minus 0.033, and this is significant. So this should be less than absolute 1 and greater than 0, and it should be significant. So this also shows the speed of adjustment. So it means that 0.033% discrepancy between the long run and short run equilibrium will be met in a will be covered in a quarter time, because this data is quarterly. This is the constant coefficient and it is significant. After this I'll check some of the diagnostic. This is the heteroscedasticity set, and this says that this value is less than 0.05, so we fail to reject the null hypothesis, so the variance of the residual is constant. This is the serial correlation test, and it says that the residuals are serially correlated, and this is the normality test for the residuals, and the probability value show that the residuals are not are normally distributed. So this is how we estimate or check for cointegration, and then estimate the error correction model, and finally we interpreted the data. So I will compare these two models. This is the long run model. This is the coefficient, and this is the coefficient for the natural log of investment. R square is 0.97, adjusted R square is 0.97, F value is 3236.66, and this is highly significant. And this is the short run model, and this is the cointegration equation or the error correction coefficient. This is less than -1, and it is significant. So this shows the speed of adjustment. If there is any discrepancy between a long run and short run equilibrium, then 0.033% of the discrepancy will be covered in a 1 quarter time. So ladies and gentlemen, this is very interesting, and I hope you like it. I thank you for your attention. If you haven't yet subscribed to the model, to the video, kindly do subscribe and click on bell icon. Thanks for watching this video.